That's about all you can see in the camera. But what you see here are 3 of 6 shelves of books on the interpretation of quantum theory, quantum mechanics. 6 shelves of them. So 1 shelf, 1 meter, so 6 meters of books on the interpretation of quantum mechanics. And if I live long enough, if I can keep doing these videos for another 33 decades, 30 years, I will give many courses, that's the intention, that's the plan, on the interpretation of quantum mechanics, because it's a fascinating subject, as I hope you'll find. Alright, moving on a bit. So in my view, and a lot of other people, two of the weirdest concepts in quantum mechanics, something called superposition. Basically, if you have a state in quantum mechanics, let's say state 1, and you also have another state, state 2, this may sound crazy, but you can add those 2 states in quantum mechanics. So a quantum system can, in a certain sense, be in state 1 and in state 2 at the same time. Now, huh? Duh. Definitely not duh. A state is a description, it's a list of numerical values of physical quantities of some system, like the position, the momentum, the charge, the mass, blah, blah, blah. Okay? So, say, included in that state description, that state, is the position. Okay? So you have state 1, and let's say this quantum particle is in position x1. And you have another state, state 2, and its position is x2, which is different, let's say, from x1 and x2. But in quantum mechanics, you can add states. So what does that mean? Interpretation, right? What does that mean? Does that mean that this quantum system can be in 2 positions at the same time? Huh? Well, welcome to quantum mechanics, right? You're starting to get a feel for how weird quantum mechanics is. Okay? So I'm just giving you a taste, right? So superposition, that just means adding states. So state 1 plus state 2 is a new, another state, like a third state in effect, and a quantum system can have that third state, which is the sum of 2 others, or 3 others, or n others, or 2 to the n others. Okay? So superposition. Entanglement, what's that? Well, in my view, and a lot of other people, entanglement is the #1 weirdest phenomenon in quantum mechanics, right? Now, I don't understand quantum entanglement, but roughly what's going on is the following. Say 2 particles, 2 quantum systems, maybe like 2 photons, bullets of light, or 2 electrons or something. They come together, they interact, they get entangled in some way, and what does that mean? Well, what it means is that when they later separate, and they may go to the far ends of the universe, hugely separated, but then if you perform, because they're entangled somehow, they've connected up in some vague sense, if you perform some measurement on this particle, this separated but now entangled particle, entangled with this one, the result that you get, you influence that first particle by measuring it, right? And what you're doing, that measurement on particle 1, this end of the universe, will in 0 time, in other words, instantaneously, right, influence the outcome of a measurement that you do on particle 2. So it's as if, well, I mean, here's where interpretation comes in. What the hell is going on? So what happens here, in other words, in 0 time influences what's going on here in 0 time. That underlined. Now that is so counterintuitive, so weird, that you pull your hair out and you say, how can nature be like that? Indeed, indeed. And yet, ironically, superposition and entanglement, or non-locality, right? So some non-local influence, like over here, can have an effect on what's happening here. So Einstein so hated this phenomenon. He talked about, well, in German, spukhafte Fernwirkung, which translates roughly as spooky action at a distance, right? Spooky in the sense of ghost-like, right? I mean, how intuitively, how can something that's far, far away over here in zero time influence what's happening here? As though they're connected somehow, these two things. As though they are somehow entangled, right? Hence the word. Now, ironically, these two phenomena are the basis, the very foundation of QC, meaning quantum computing. Now, that's one of the reasons why I'm so fascinated by quantum computers. Firstly for huge power, right? When we finally get scalable quantum computers that scale up to large numbers of qubits, as they're called, quantum bits, bits of information, 0 or 1. But because of superposition, your state, you're in state bit 0 and state bit 1. Because of superposition, you can add those two states, right? So quantum computing, you have hugely more power to compute with than with a classical computer. So quantum computing promises to outperform classical computing by a factor of 2 to the power n, where n is the number of quantum bits that you have. For example, a quantum bit might be an electron spinning one way, that might correspond to a 0, and spinning the other way, that might correspond to a 1, state 1. And because of superposition, you can add those two, whatever that means. Okay. All right, well, let's do a little bit of history now, sort of change the topic somewhat. Quantum mechanics, when did it start? Well, the father of quantum mechanics is Max Planck. Planck, German theoretical physicist. He was looking at the so-called black body radiation problem. What is that? Well, take a piece of iron, I-R-O-N, iron, and you put it in a fire and it gets hot and it'll glow red, right? Now, if you blast oxygen at it, so it gets really hot, its color will change from red to yellow. And if you really blast oxygen at it, it can get white hot, right? It's so hot that it glows white. So in other words, this hot body is giving out radiation, light, of different colors. Well, you can measure the distribution of the energy for a band of wavelengths or frequencies, and you'll get something. In reality, it looks a bit like this, right? So here's the frequency of your light, and this is the intensity. How much of your radiation comes out at this frequency or that frequency, right? So this is a distribution of frequency of the light, and Planck was looking at this phenomenon. He wanted a formula, a mathematical formula, physics formula, that gave him this distribution. Right, now he found it, but he sort of cheated. There were at the time two different theories trying to explain this phenomenon, and one was sort of like it was quite good at the low frequencies, but then it sort of shot up to infinity. It went horribly wrong. And there was another theory, a second theory, that was quite good at high frequencies, but shot up this way. So it was very bad when the frequencies were low. Now, Planck knew this. His specialty was thermodynamics. And later, he tried all kinds of things and nothing really worked. So then he turned to statistical mechanics. He absorbed the ideas of Boltzmann, Austrian theoretical physicist. Anyway, he took these two formulae and combined them. So in a kind of fudge, a mathematical fudge. So he found a formula, the famous Planck black body radiation distribution formula, that gave him this and this. So he found a formula for the real world phenomenon, the real world behavior of light coming out of a hot body, right? And then he started looking at, interpretation. So he had the formula and he started thinking about what it meant. And he came to a radical conclusion, and a lot of historians feel that Planck himself did not fully grasp the full import, the full importance of what he'd discovered. And the conclusion that Planck came to was that he modelled matter, the atoms, as harmonic oscillators. They're just like little particles that oscillate like this, right? So, and when light was shone onto this matter, Planck's conclusion was that the energy of the light would be exchanged, transmitted to the matter, not continuously. If you assume that the light energy gets transmitted or absorbed by the matter continuously, that's classical mechanical thinking. Right? That's classical mechanics. And that's what everyone had assumed until Planck came along in 1900. But what Planck was suggesting now, this radical new hypothesis that shattered classical mechanics with hindsight, with 20/20 vision, there was a kind of exchange of energy from the radiation, the light, transmitted to the energy of the particles in quantized energy lumps. And these little, like the light would give energy to the matter, right? In a sense, the energy of the light is being absorbed by the energy of the matter. The energy of the matter goes up a little bit, and the energy of the light goes down a little bit. Energy is conserved, one of the basic laws of physics, right? So what one loses, the other gains. A zero-sum game. Okay, but this energy exchange between the light and the matter occurred in energy lumps, in a quantum of energy. And hence this notion of quantum mechanics, right? And then, so that's 1900. And then along comes Einstein 5 years later, a very young man, 26 years old, working in a patent office in Bern, in Switzerland. Einstein's studying Planck avidly and others, and comes to the conclusion, now wait a minute, the energy, so Planck's conception, his vision of what was happening was the light can take on any energy level, right? It's continuous. Planck was thinking classically, and the energy level of the matter also has continuous values of energy, but the exchange, like the transmission of the energy from the light to the matter, that was